Okay, second case, I'm going to let k equal 6. So we're solving this differential equation. And again, solving of it's quite straightforward, especially when these equal 0. So we've got m squared plus 6m plus 25 equals 0. You can just pop that into a calculator and you end up with m is equal to minus 3 plus or minus 4i. And so the general form for that is e to the minus 3t a sine 40 plus b cos of 40, like so. And then we can use initial conditions to find a and b. So t equals 0, x equals 0, sine of 0 is 0, cos of 0 is 1, e to the 0 is 0. And so from here it follows that 0 is equal to b, which I'm going to substitute straight in because it does just make all of this a little bit easier when b is 0 to then differentiate. So I've got a e to the minus 3t sine of 40. Differentiating, so you might have to do a bit of product rule differentiating through these examples. So differentiating the exponential part, I've got minus 3a e to the minus 3t sine 40, and then differentiating sine of 40, I get 4a e to the minus 3t cos of 40. Write that out in fuller if you'd prefer to. And then when t equals 0, the velocity is equal to 1. The velocity is dx dt, and so 1 is equal to, this all goes to 0, and so 1 is equal to 4a, and a is equal to a quarter. Substituting that in, x is equal to a quarter e to the minus 3t sine of 40. So this actually oscillates. If you think about what happens as t increases, sine of 40 is, we've just got this sine wave with a stretch scale factor of a quarter in the x-axis. So that's just doing that. Sorry, it's not very neat. The quarter will just stretch you by a quarter in the y-axis. The e to the minus 3t will approach 0 as t gets bigger and bigger and bigger. That will approach 0 relatively quickly, actually. And so, sketching this, the period is equal to 2 pi over 4, because we've got a stretch scale factor a quarter in the x-axis, which is pi over 2. I'm not going to do a super neat sketch, but do pop this into GeoGebra if you want to. When x is 0, t is 0, so it's going to start on the origin. And then we'll get the sine curve with period pi over 2, with then a decreasing amplitude. And so that would be oscillating towards 0 as t approaches infinity. And so this will be the case for all damped harmonic motion where you have a negative discriminant, so you've got two complex roots. So what we've sort of worked out from there is, so if the discriminant of the auxiliary equation is less than 0, then oscillations will occur. And this is called light damping. You may also see that called underdamping, depending on which book you pick up, to be honest with you. But I think light and heavy damping are kind of easier words to use there. So that's that one. And we just need to look at where the discriminant equals 0, but I'll do that on the next one.